Okay, so we're going to do 2 article summaries. Now, in most science classes, this is kind of the main thing that at some point we have to begin to read journal articles, right? We have to be able to get used to being able to read journal articles. And again, we don't often get a lot of time to do this other than when we're in science classes. And in the summer, we're not doing a research paper. So the research, we don't spend time in the library doing a lot of research. And so I kind of use this as kind of an intermediate assignment, both during the regular semester and during the summer, to give you a short view of where you can do a little bit of research, as in finding information and then reading a journal article. All right, so if you're on the article summary page, again, this is right from the home page. Okay, if you're straight on the home page, you can go right down to the journal article assignment. All right, now there is a sample on here. Okay, so if you click on review an article example, all right, so you'll see here, it's not very long, right? It's 2-3 paragraphs at most, right? So it's giving the citation, who's the authors, the title, the article summary, the article citation, and then going through what is the background information, what is the purpose or problem that they're trying to get at, and what did they find, and then down at and then at the end, if we were going to talk about the article in class, what might you put forward as a question to help conversation? Like if we were going to talk about it, what might you use to kind of spur on some conversation, right? So a question or two, right? So this is pretty simple, right? So it shouldn't be too long. Oh, lost my. All right, so in order to do this, okay, you're not just picking random articles. You are using my articles that I have cited for you here. Now, I will probably add a few more over the next week, right? So before you start doing this, I will, in the next day or two, I'll probably add some additional articles, right? But these are articles that you can find on the Nova Library, okay? Now, there is a link for the Nova Library. All right. Now, if you've never done or used the Nova Library, you're probably going to have to rewatch the first part of this video again, right? But you want to click on the Nova Library, right? That's going to bring you to the main Nova Library page. Okay. Now, from the library page, there is a link on articles. Okay. And they give you recommended databases where you can find a variety of articles. Now, you can obviously pick databases by subject. If you know which kind of, if you're going to search by chemistry or, science journals and things like that. But where I recommend you start is just the very first link, Academic Search Complete. Okay. Now, when you log in, when you click on this from outside the library, you'll have to log in with your Nova login, right? So you log in with your Nova login. And then you'll have basically an easy search engine here. And this is really, it's not too difficult to use. This thing is linked to a whole bunch of different databases. So you can actually click to have it search all of these different databases. So Academic Search Complete is linked to all these different databases that you can search from. Okay, so usually I'll just click on all of them, and then it really kind of casts a wide net as to what you want to look at. All right.
Professor Jensen?
Yes.
Sorry, so from the library, Nova Library, what did you click for the recommended database? Is it like the databases by subject or A to Z?
Now, if you pick on articles first,
yeah,
and then Academic Search Complete.
Gotcha. Thank you.
Right. So the academic search complete, I mean, this is a great source. No matter what kind of research you're doing, it'll get you to this EBSCO host. So in most universities, you have access to a library, and most universities pay for a library access. So if you go to Virginia Tech or some other larger university, they will have a much more robust version basically of this. Like I guarantee you can find this same EBSCO host database at the library, whatever university you might go to. This is the same one we used at Mason when I was there. It's the same one that that Nova has, and really each university just pays for a kind of subscription to this database. Now, some universities pay for a more robust access to a variety of journals or a variety of other databases, and so they may be larger than the Nova database. But you know, my organization, like we pay like 60 grand for like access to like a few journals, and you guys as students have access to all of that and more through this one place. All right, this is a kind of a one-stop shop for all kinds of research. Whenever I'm doing research, this is the main place that I go to. Right, and so you have to try and find. So your goal here is that you want to find one of these. Okay, now obviously this, if you've done any type of just Googling in general, you can usually find your way around finding these, and it may just take a minute or two to find, depending on how you want to search, whether you just you do the whole title or whatever. But if we do a search for a journal article, so let's see the example one that I used, right? So and so you'll probably be able to find the full article. All right, so I've guaranteed that all of the articles citations there, they are in the library. So you just have to find them, right? And so you can look at, so there are a variety of search criteria that you can do. If you want to find peer-reviewed journals, you want to have the full text, it will update and give you access to just ones where you have the full text. If we want peer-reviewed articles, so if you want to do research on any other kind of subject, peer-reviewed articles are always a great place to start. And so when you find the article, you can go into the article and they have the full PDF text that you can download. Okay, so a lot of these, you'll find an abstract. You really kind of have to be in here because it is unlikely that you're going to find enough information by Googling these journals. Okay, you're probably not going to find these on Google Scholar, right? Or not going to find enough. You may find abstracts and things like that, but these are free on the Nova Library. Okay, and then you can click on the full text. You can read through the text, which is what I want you to do. Read it and give me a summary of it. Okay, and so from the articles, you can go to the academic search complete, and the EBSCO host database should be able to get you any one of those. So you just got to pick one that you find interesting. Okay, just find one that you find interesting out of the list. Oops, went too far. Okay, so I put a variety of stuff in here. So again, you can pick through, and I'll put some other journal articles on here as well. So there's a variety of other journal articles I'll put on here that I have to just check through the library to make sure they have. But there's a variety of stuff that you can search for. Okay, so just pick one and do a summary of that one article. And then that one article summary will be in a Word document that you'll submit under Journal Article Review 1. And then you'll pick a different journal article for your second time around. And then you pick a different article, read the second article, write a short review. Again, the title and author or the full citation, what is the purpose of their research? What is the background issues they're looking at? What did they find? And then the discussion questions. Okay. And so again, most of this is relatively easy to search through. These articles are not super long. So I didn't pick any in here that are like, 45-page review articles and things like that. So you're not likely to find too many of these that are too long. So, I mean, like you say, you can look at the page lengths and see, okay, it's, 10 pages or 11 pages, 10 pages, 9 pages. And so they're all about the same rough length so you can read through them and pick out the important parts, summarize them in a Word document, and then upload that. Okay. So that is the article summary that I want you to do. 2 articles, 2 of these articles, and I will add additional articles here in the next couple of days.
And sorry, just to confirm, the due date for the first one is June 8th and the second one is June 22nd?
That sounds right.
Okay.
We can check the calendar here real quick. So let's see. June 8th, yes, the journal article 1, and June 22nd is journal article 2. Okay. All right. Next, let's talk about the physical properties lab. Now, we don't have class on Monday, okay, since it's a holiday. So my goal is that every Monday, since it's technically our lab day, that I would talk about the next lab that we're going to do. So we're going to talk about that now. All right. So let's look at the physical properties lab. Okay. So you're working on the pennies lab. The physical properties lab is the next one. All right. And so you will have, so all the information that you need is in these 3 links. Okay. So the physical properties PDF is my handout that we would use if we were in the lab. Okay. So this is the methodology, the procedure section, the data set, the pre-lab questions are in here. Okay. Here's your pre-lab questions. Here's the data table that you would have. And we're only going to do part A of this. So we'll get to that in a minute here. All right. So, but this is the PDF that we would have if we were going to do this in the lab. Okay. So this is where you would get things like the procedure. Okay. So here is the procedure section that you would use for your report. Okay. We are only going to do part A. Okay. So only part A. I'll add an extra note into the to the section that only part A. Okay, we're not doing the density, the metal for part B. Okay, so this is the procedure section here that you would want to take out and use in your procedure section. Again, you can bulletize this and put these in bullets. You can summarize it. You can read through it and pull out what you think was important steps that would have been made. You can summarize these into a few shorter steps. Instead of doing 18 steps, you could summarize this into like 5 steps or so. You can just copy and paste these steps into your section. What I don't want is this PDF filled in like it's a tax document and given back to me. Okay, you start your own document and write your own report. All right. You can just use this as a guide. It is a guide to get you towards your report. Okay. So the data table down here is a guide. These handouts have data tables as a guide to give you the kind of information or get you used to what kind of ways should you organize if you were collecting data in the lab. Okay. So, because oftentimes, if you were like me when you were in the lab, you just copy down numbers all over the place. And then a week goes by and you go back and you look at your notebook and you can't figure out what numbers, what any of that meant. right? So your note-taking skills were terrible. And so this is a guide to help us to organize and begin to learn how we would gather information and organize it in such a way that we don't lose track of what information we have, okay? Now, I've given you a, let's see if we can go back to this. All right. So there is a link here with the physical properties information. So a lot of this is going to be the same stuff I'm going to cover here in a minute. Okay. But the third link there was an Excel sheet. So let me switch over to that. Okay. So here's the Excel sheet that mimics the data table. Okay. This mimics the data table that's in the PDF. Okay. So if you look at the PDF data table, this is the same setup of data table. So I filled in here the important information that you would need in order to do the lab. Okay, so this is essentially what we would have collected, the data that we would have collected had we been in the lab. Okay, so measuring the empty flask. Okay, so in this experiment, we are measuring calcium chloride. Okay, so that is the purpose of this experiment is to determine the concentration of an unknown calcium chloride sample. Okay, it's not an unknown that we don't know what it is. It is an unknown in that we don't know what is the concentration of the calcium chloride. Right. So there are various samples in here, like the weights of various flasks, which you would have to be in the lab to measure weights of various flasks. Right. So these would be data that you would physically have to be there to collect. So this is what I've given you in order to do this. Okay. So let's look at let's go back to the, all right. So right here, I've identified the purpose of the experiment is to determine the percent composition of the calcium chloride unknown. All right. Now let's look at the handout here. You'll notice the purpose is very different than the stated objectives. Okay. This is where I was talking about the other day, where the objectives listed in the PDF of the handout are not strictly the purpose of doing the experiment. Okay. That when we are in the lab, okay, and usually this is a longer lecture of when we're in the lab of how we do this, that when you're in the lab, you're writing these lab reports, we would be focused on a customer driven approach. Okay. So the objective or the purpose is not to become familiar with laboratory tools and techniques by measuring physical properties such as density. The purpose is not to determine the densities of several pure substances and mixtures. Okay, that is not why we would do it. Okay, so this would be like saying the purpose of getting a blood test is so some technician can learn how to do a blood test. Okay, that's not why you would give blood. That's not why your doctor would ask you to give a blood sample, right? They would want to ask for a blood sample in order to use it as a way to diagnose something about your health. They're not collecting data simply that the lab people can learn how to deal with it. Okay. And honestly, that's not what you would go to the doctor for. You wouldn't want to go to the doctor to find out that the nurse drawing your blood, that was the very first time they've ever drawn blood, right? Their purpose of drawing blood was not to practice on you drawing blood, right? That would not inspire confidence if your nurse came in and said, I've never done this before. My objective here is to learn how to draw blood. Okay. We are assuming that that the purpose is similar to what we would do if we were in the lab. Okay. Our purpose is to analyze the sample for the concentration. Okay. We want to get at the concentration of an unknown. Okay. So that is the purpose here. Okay. to determine the percent composition of a calcium chloride unknown. All right, so this is very similar to what we would do in an environmental lab. Okay, when I worked in an environmental lab, we got in water samples. We already know that stuff is in there. Okay, we know there's calcium chloride in the sample. Okay, so it's not an unknown. We know it's in there. The question is, how much is in there? Okay, so what we would do is we would set up a calibration curve. Okay, so usually this is done from instruments. So an instrument would measure a response of whatever it is you're looking for. Okay, in this case, we're using density as our response, right? And so a calibration curve is where we would set up standards that we know what the concentration is. Okay, and so we are testing with the instrument's response to various concentrations that are known. Okay, so you have a set of standards, one that's 10%, one that's 20%, one that's 25%, one that's 30%, one that's 40%, and one that's 50%. And we're seeing how the instrument responds to a change in concentration. As we change the concentration, the response from the instrument goes up. In this case, the density goes up in a linear fashion with the concentration. Okay, which is what you would expect, right? If your instrument is keying off the ions being produced, okay, in some instruments, as we use a an ion flame, and it hits the sample with a high intensity flame, and it is measuring the ion response of the sample. Now, the more ions you have, the larger the response the instrument's going to get, right? This is a logical thing, right? If I have more stuff, I'm going to get a larger response in my instrument. Okay, so same thing here. If you have more calcium chloride in your sample, your density is going to be higher. Okay, you're going to get a higher density as it's more concentrated. There's more salt dissolved in the water. Okay, if you think about if we were making standards, we'd have 100 milliliters, 100 milliliters, 100 milliliters, 100 milliliters, and you would scoop salt into each one. And so you would just keep scooping salt into the higher ones. And so I'm not changing the volume. The volume doesn't change. But what changes is the amount of salt dissolved. So that's obviously going to change the mass of each sample, but the mass is going to go up commensurate with how much salt is in there. And so that obviously affects the density. So a higher concentration means it's going to have a higher density. Okay. And so we create a calibration curve of samples that we know what their concentrations are. Okay. And usually an instrument would create this graph on its own. It wouldn't actually create the graph. It would create the data for it. And then it gives you a trend line. Then you're going to do a trend line. Okay. And you're going to see what this looks like in a minute. Okay. In Excel, we would do a trend line. And it would give you the equation for your line. Okay. With this equation, okay, with this equation, y equals mx plus b, okay, and that is the equation for a linear graph, okay, for a line, y equals mx plus b, y, the slope, x, the y-intercept, right? So again, most everybody should have had basic algebra before you come into this class. Y equals mx plus b this should not be the first time that you've ever seen this, all right? So y represents my density. X represents my concentration, right? And then we would do an unknown in the same way. My unknown, I would measure its density. Now, the whole purpose of the calibration curve is that I'm setting up a curve in which we expect my unknown to fall between the low and the high, okay? That is the purpose of a calibration curve, is that you expect whatever you're measuring to fall between the 2 points. Okay, so everything should fall between 10 and 50. Okay, so I'm expecting my unknown to be between 10 and 50. Now, obviously, if it doesn't, you have to go back and redo your calibration curve and then reassess your unknown. Okay, or you dilute the unknown. Like usually the issue is like you know, my unknown spikes way up, you know, up above. So I'd have to go back and run it again at a more dilute in order to bring it within the range for my calibration curve. So the calibration curve only works between the max and min, right? So it sets up the high and low points, right? So I expect somewhere my unknown to be somewhere between the high and the low. Okay. So your density, so you have the density of the unknown. Okay. We would measure the density of the unknown. Okay. We don't know its concentration. So with this equation, you would plug the density of the unknown, which is a numerical value, in for y. Okay. Now, if you plug that in for y, the only value you don't have now is x. Okay. So if I plug my density of my unknown in for y and I solve for x, it would give me the concentration of my unknown. Okay. So that is essentially what we are doing here. All right. So you have the data. So you are going to prepare a calibration curve of the data. And then you are going to calculate what is the concentration of the unknown. All right, so let's look at the data table again. Okay. Now this is the data that you're given. Okay. The mass of the empty volumetric flask with stopper. Okay, so this is the glassware. How much does the glassware weigh empty? Right? This is the mass of the flask with the 10% solution in it. Okay. Now, what are we measuring? The density of. We're measuring the density of the solutions. I don't want to know the glassware's density. Okay, so what do we think this logically means here if I'm going to get to the solution itself? I have the empty flask and I have the flask full of water. You would want to subtract these two values in order to get the mass of the solution. Now, since these are 1 milliliter, so the volume, so the flasks that we use were like just little tiny baby little 1 milliliter flasks. So all of the samples were already 1 milliliter. So the mass of each solution is the density. Okay. But, okay, however, let's look at the sig figs. Okay, we talked about this last night, significant figures. How many significant figures do you see in this number? 26.974. Five, very good. So there are 5 sig figs in this number. The volume has 3 sig figs. So if I have 5 sig figs as mass and I'm dividing by volume with 3 sig figs, my answer should have how many sig figs?
3.
3, exactly. So we should have 3 sig figs for our densities. Okay. Very good. So keep that in mind when we're doing our calculations. This is usually something what I harp on in the lab is it really when I am looking for significant figures, again, the tests have the right sig figs for everything. So I'm not really concerned about the sig figs on like the tests and stuff. So really my concern of sig figs is when we're in the lab using the equipment or when we're doing calculations based on actual data that we got from the lab, that we should have the proper number of sig figs from our equipment, right? So this means that technically our solutions are about, so you would want to use 3 sig figs for your solutions, right? So again, the standards are, 0.0 solutions. So your answer is essentially going to be out to 3 sig figs. All right, so how do you know which unknown you have? Now I've put 3 unknowns in here, okay? So here's how you're gonna do it. If your last name starts with an A or your last name or through the letter J, you will use unknown number 1, okay? That is your unknown. If your last name begins with a U through a Z, unknown number 3 is your unknown. Okay. If your last name is K through T, starts with a K or starts through a T, unknown number 2 is your unknown. Okay. Now in this case, again, there is a right answer. Okay. I already know the answers that go with this because I've given you the data. So this is slightly different than we would do in the lab because, like I said, I would be less concerned about that you got the right answer because I would believe that you got the answer, or I would accept the answer that you have, except in this case, I already know the answer. Okay. So when you get the densities, okay, of your solutions, you would want to plot. Okay, so here's an important thing to note. Okay, you are only plotting data of the 10 to 50% solution on your graph. You do not, I repeat, you do not graph the unknown. You do not graph the unknown. Primarily because you can't, right? If we know the density, that is one coordinate, right? On a graph, there are at least 2 coordinates, right? In a 2-dimensional graph, you have X and Y. We only have 1 coordinate. So there is no way that you can functionally graph the unknown, right? So the unknown should not appear on your calibration curve. I do not want to see some random, other data points show up on your graph. Okay. These solutions, the 10 to 50% solution, are the only thing that should be on your graph. Okay. And so your graph, okay, I made up some data here, and this is what my graph looks like. Okay. Now, if you do this, okay, so here's essentially how I put this together. Okay. So here's my 10, 20, 25, 30, 40, 50. You can do this lengthwise. It doesn't really matter. You got to make sure that the graph is is pulling the right X and Y values. What do we write in the second row? All right, well, that's, you're talking about the mass of the solution. So this is the mass. So the first row is the mass of the flask containing the solution. Okay, so that's the glassware plus the liquid. This is just the liquid, right? So I would want to get rid of the glassware, which you have the mass of the glassware up here, the mass of the empty flask with stopper up here. Okay, so the difference from this number here to this number here, so this is obviously more, right? Because it has liquid in it. This one's empty. So if I subtract this out, the difference between this and the empty glassware is just the solution. Okay, so that is the mass of the solution. That's what's the second row data. Okay, it's the mass of the solution. All right. So here what I did was I took my densities. Okay, so I made these up. So these are not going to be your density values for these solutions, right? So here's the 5 solutions or 6 solutions. Here's my 6 densities that went with it. Okay, so if you highlight these, okay, if you set up this as X and Y, it's easy. Excel understands this easier if you do this as X and Y, right? So you put your X values and your Y values together like this. So here's my X value is my density, my Y value, or my X value is my concentration, my Y value is my density. Okay, so if you go here and then we want to insert a new graph. So again, we should be practicing our graphing from our, many of you are probably understanding what your limitations might be in doing your graph from the Pennies lab. So again, here I want an XY scatter plot. Okay, XY scatter. Okay, just the data points. Okay. We don't, you don't need the smooth lines, no lines, no lines, no lines. Again, if you want your graph with the, all the lines connected, I can give it to my 5-year-old and he can connect it with a crayon for you. Okay. We don't need to connect the dots, right? So this gives us a basic graph, all right? Now in Excel, one of the easy ways to do this is to pick a quick layout. Now, there is a quick layout that is exactly what you want, okay? In most Excel layouts, you'll probably find layout number 9. This might be different in your Excel, but in my experience, depending on no matter which computer I go to, layout number 9 tends to be very similar when we're looking at Excel, provided that you have a real copy of Excel. Okay. And that gives you the trend line. It does everything for you. Okay. You just got to clean this up. We just got to clean this up so that it looks more like, this. Okay. This looks better. Okay. The axes are nice and labeled. They are readable and large enough. My axes are large enough to read. Okay. My equation is large enough to read. I can see my data points. I can see my trend line. Okay. Now there are a variety of YouTube videos. Yes, this video was posted on Canvas, so you can refer back to it, yes. But there's also on Canvas, there are videos in here on how to do a trend line, okay? Along with the other videos on how to do a basic graph. Okay, so this video goes over how to do a chart and how to do a trend line.
Sorry, so you said, are we including a line or no? Because at one time you just said not to include the lines, but then you said a trend liner. So the 2 separate graphs, or?
No, a trend line is different than connecting the dots to make lines on your graph.
Okay.
Right, so the trend line is a linear best fit line. Okay, so it is a line, but it is a best fit line that best represents where your data is. Okay, so it is not going to look like this. Let's go back here. So what I was saying is I don't want is like this, right? So when you do this, this is connecting the dots with a line, okay? The trend line does not connect the dots. The trend line fits the data to a linear fashion. Now, the more linear your data is, okay, that's what you're going to see this R squared value is over here, okay? The R squared value is a relationship of how linear your data is. So the closer to 1, the more linear your data is. It's kind of like a QC check or an error analysis check. So if your data was not close to 1, like for example, let's just change one of these. Let's say this is, right? So you see that it gets less from 1, or it's starting to go down because the data is slightly off. So it's kind of like looking at the standard deviation, right? So from the Penny's lab, when we looked at standard deviation, how far off of the average is it? So the trend line puts, and so you also saw the equation change, right? The equation changed when I changed the data point, right? Because it is trying to create a line that best fits my data. Okay, so this is a separate kind of thing than connecting the dots with a nice smooth line. Okay, so you should have a trend line, not connecting all the dots with a line. Okay. And then you have over here your unknown. Okay. Here is your unknown. So when you get to your unknown density, okay, you're going to have a number right here. That's the unknown's density. The unknown's density is found the same way as all the rest of them. You have its mass. You have the empty glassware. If you subtract the two, you will get the mass of the solution. So you'll have the density value here. This density value goes in to y. So you're going to have to do this on a separate place. Plug that density in for y. And the only thing missing then is the x value, okay, which is corresponding to the concentration. What is the concentration of this unknown in percentage? Okay. Now, all right. This is important, okay? So once you get your density of your unknown, once you have a graph and an equation, and you take your density and plug it in for y, okay? This is an analytical experiment. We took time to use analytical pieces of glassware. We took time to measure out each sample with an analytical scale that reads 4 or 5 decimal places. Your answer should not be about 30%. It should not be about 50% or around anything. Okay, I am looking for a specific, exact answer. We are doing math. When you do math and you go to a math class, you don't do a calculation and tell your professor the answer is about 5. Okay, there are decimal places that go with answers. I want a real answer. Okay, if you go and get a blood test, your doctor does not say you are kind of healthy. Okay, you may or may not have liver cancer. Right? That is not an analytical test or answer that you want. Your water has about an unhealthy amount of lead in it. That doesn't really inspire confidence if you are drinking water that has lead in it, right? You want to know how much lead is in your water, right? How much lead's in my water? It's about a ppm, maybe 2. I don't know. It's around there. Somewhere between 1 and 10 ppm, for sure. Okay. That's not an answer that you want. Okay. You're not paying someone to do an analytical test of your information to give you a range of stuff that's between, you have somewhere between a cold and COVID-19. Somewhere around there. One of those two. They're kind of the same, right? I mean, they're kind of the same, right? That's not the kind of answer that you want, okay? That's not the kind of answer that we get in science, okay? So I am looking for an exact answer, okay? So you should give me an exact number with as many significant figures as you are supposed to give me, okay? If all of your data yields 3 significant figures, your answer should therefore probably have 3 significant figures, okay? Even if your third significant figure is a 0, okay? If it is 40%, it should be 40.0%, okay? So the purpose of this experiment is to determine the percent composition of the calcium chloride unknown. You have this page that goes over this information. You have a PDF that has the procedure. The PDF has the pre-lab questions. Okay, you need to copy these into your report, the pre-lab questions. Okay, you have a data table that you would copy into your report. Now, I've already given you an Excel sheet copy, so more than likely, a lot of you are probably just going to copy the Excel sheet, which is fine, right? But, you know, again, I just don't want to see my PDF. I don't want to see this PDF, right? The Excel sheet is going to look the same whether you did it or I did it, right? So, but in this case, I don't want to see my PDF given back to me, okay? So I don't want to see this, right? Whatever you have to do to make it not this, that's what I want, okay? Which includes probably putting into a Word document, copying and pasting all the tables in there, copying and pasting the graphs in there, making it look nice, working on our soft skills. Okay, I know this is a chemistry class, but that doesn't mean we can't make it look good, right? If you're giving this to your boss, okay, what does your boss want to see? Okay, if you did it in crayon, is your boss going to be happy with that? Okay. All right. Questions on the 2 assignments?
Those 2 assignments were the journal and the lab.
Right. The journal assignment and the lab. Yes. Okay. So what we're going to do is we're going to take a 4-minute break. Okay. Until 7 o'clock. I'm going to get set up to do some practice problems so we can take a look at a few other density conversion things, and then we'll wrap up chapter 1. All right. So I'm going to probably pause my video here for just a minute while I get my computer set up to do some practice problems. Okay. All right. So we're going to, let's get to the, okay. So one last time here. We have 4.15 grams per milliliter. This is a stated density. We're told that the solution has 673 grams. And we want to know, what is the volume of this solution? Okay. What is the volume? So when we're doing this, density, we can look at this as density as a conversion factor between mass and volume. Okay. So you can look at it as how you would solve this. How you're going to solve this is really just a rearrangement of this equation, right? We want to solve for volume. So we bring the volume over here, divide the density down, right? So realistically, if you're solving this and you just want an answer, we just want the answer, it is the mass divided by the density, okay? That is the quick and dirty answer for how we get to the answer. It's just the mass divided by the density, okay? But we want to get to more than that. We want to know, we want to better understand what are happening to the units. So when we're working with problems like this, the best way to do this is to start with the simplest term, okay? So this is how we'll start many of these different problems. The simplest term here being the gram unit versus the density, okay? Density is made up of 2 terms, gram and milliliter. So there are 2 terms versus 1 term. So 1 term is the simpler term. So that is where we're going to start. Okay. This density here is not written as, right? Then the question becomes, well, what happens to the milliliters really? All right. But it's not really this. The milliliter is really becomes on the top, because this is actually 4.15 grams for every 1 milliliter, right? That's the the real way this is being presented. And so if this goes here, the bottom part flips up to the top, right? And so by dividing grams by itself, I get rid of the gram units. And so the only unit that's left is milliliter. So when we do the division of mass divided by density, we are left with a unit of volume. Okay, and so when we do this, again, I don't have these done in advance here. So 673 divided by, and we're gonna multiply everything on the top, divide by everything on the bottom. So I'm just dividing by the 4.15. And I get 162.168, right? Okay, so of our stated values here, okay, of our stated values, how many significant figures should our answer have?
3.
3, right? So we have, more or less 3 numbers, 3 sig figs here, and we have 3 sig figs here. So our answer should therefore have 3 significant figures. So we go 1, 2, 3, and we'd make the cutoff right there, right? And so the next number, we would standard rounding rules would apply here, right? And so since this is a 1, we would cut off these other ones, and we would go with 162. So it's 162 milliliters as our answer.
So if a number had 4 sig figs and then one had 3, do you go with 3 or 4? 3, okay.
3, right. So when we're doing division, okay, the fewer number of significant figures drives the answer. Okay. So let's look at a second one here. Okay. All right, so let's look at, okay. Mercury, Hg, has a density of 13.53 grams per milliliter. Okay, mercury. The symbol is Hg. Okay. Mercury has a very high density. If there was 12.1 milliliters, how many grams of mercury would I have? Okay, how many grams of mercury would I have? We have 12.1 milliliters, and we have the density of mercury. We want to know how many grams of mercury would that be? Okay, so we know the density is mass divided by volume, right? If I want to solve for the mass, I'm going to multiply my volume. So mass equals density times volume, right? Provided that my volume is the same unit as my density, right? That's the key. That's the only, that we saw this one last night where we had the density was in microliters. And so we couldn't just take the density times the volume. But if they're the same unit, we could just multiply it. Okay. So here we're going to start with our simplest term, okay, which is the 12.1 milliliters. Okay. And we're going to multiply my density, which is the 13.53 grams per milliliter. So the milliliters being divided by one another go away. So when I multiply density times volume, I end up with a mass unit. Okay, now when we do this multiplication, again, we're going to multiply all the numbers on the top. Okay, and my calculator gives me 163.713 grams. Okay. So we have 3 sig figs. We have 4 sig figs. When we multiply, the fewer number of significant figures is the driver. So our answer should have 3 significant figures. Okay, there are 3 sig figs right there. So that's 7 then. Standard rounding rules we're going to apply. So my answer then, if we're applying 3 sig figs, is 164 grams. Okay, best and final answer. Okay, we'd round that last digit. Okay. Everybody follow that one okay? Let's look at another unit conversion. Okay, let's look at a unit conversion one. Okay, so here we have a density expressed as kilograms per meter cubed. And we want to convert this unit to grams per milliliter. Okay, so there isn't a simpler term. So we are starting with the density here because it is the only term we're given. Okay, so here it doesn't matter which unit you start with. Okay, so we have to convert both units. Okay, both units are being converted to something else. Okay, so here, you know, I never give myself enough room when I write this. So try and move this over just a little bit here, right? So I'm going to start with the kilograms first, okay? Just because, right? So in 1 kilogram, I'm going to set my unit opposite, okay? Because that's what's going to lead me forward is setting the term opposite, okay? So wherever I'm deciding to start, that term is going to go opposite. 1 kilogram. So the question is, what is the relationship here when we want to get to grams? So this would be something you'd have memorized. 1 kilogram, there are 1,000 grams. Okay, this is a metric conversion, right? 1 kilogram is 1,000 grams. So I'm just setting them opposite, or setting them equal to one another, top and bottom. Okay. By dividing by the same unit, it disappears. So if I stop right here, I would have grams per meter cubed, but I don't want the meters cubed. All right, I want milliliters. Now we saw this in the same conversion. We did something very similar to this last night. Okay, I want to go from meters cubed to milliliters. So in this case, we know the relationship that a milliliter equals a centimeter cubed. Okay, so it is easiest to convert 2 centimeters cubed, which then is a milliliter. All right, so in 1 meter, okay, I'm setting my term opposite, okay, so I know where it's going to go. In 1 meter, there were 100 centimeters. Okay, that was the linear conversion that we had memorized, okay, or you would have memorized. Okay, but a linear unit is not a volume unit. So in order to convert a linear unit into a volume unit, we have to cube the whole conversion.
I'm sorry. I keep getting lost. Where did you get the centimeters from? Like, I don't know. I just got lost when you got to that.
Okay, so these would be on the chart in the PowerPoint, right? So these are metric system conversions.
Yeah.
So this is what I said. You probably have to memorize these.
Yeah.
Okay? These were two charts that I gave, right? And so I gave you the chart that essentially breaks down the different units in size from smaller unit to larger unit. And so knowing that in 1 meter, there's 100 centimeters, okay? This is a metric system conversion, okay? This is a number that you would have to have memorized, okay? So that's why these are kind of coming out of the blue, because you will have to have these known, okay? I'm not going to give you the metric system conversions, okay?
Okay.
Right. So once you want, and again, it's stuff that you have to work on, right? So it's not, you're not having a quiz right now, right? The quiz is not till next week. So you have some time, but it requires that we have to put some effort into the memorization. We'll take a look at that one slide and I'll tell you which slide it is.
Okay. Thank you. I'm sorry.
No problem. No problem. I mean, again, these are, there's stuff we just have to commit to memory for some of these things. Again, the US units, if I was giving you, if we were going to centimeters or inches or something like that, I would give you the conversion for that. Okay. So in this case, we're going from meters to centimeters. And so in this case, you would have this value memorized that there is in 1 meter, there's 100 centimeters. And then this is the linear unit that we cube to make a volume unit. So when we cube everything in here, okay, this becomes 1 cubed, meters cubed, 100 cubed, centimeters cubed, right? We cube all the terms. Okay, and so then we multiply all the numbers on the top, divide by all the numbers on the bottom, and then we would end up with a single unit in grams per milliliter. Now, I'm just going to make the assumption here that we understand, this relationships here. So this is the same as saying milliliter, right? So I don't need to do another step to do this conversion. Okay. So let's put this in our calculator and see what we get. Okay. I'm going to multiply all the numbers on the top. Now you may have to do the 100 cube separate. Okay. Or like I said, if you're using your calculator like this, all right, parentheses are always your friend. So 2.05 times 10 to the third, okay, times 1,000, right, divided by 10 to the third, or I'm sorry, no, it's 100 cubed. Right. So again, parentheses in there help to kind of consolidate information. Right. Okay. So, shall we do a hard one? Let's find a hard one. Just in case this wasn't, Yes, exactly. So 1 meter is 100 centimeters. So actually, let's take a quick look at the, so let's take a quick look at the PowerPoint that where you're going to get that information. Again, the slide that you need to focus on. So let's, okay, just so we don't.
Quick question.
Yes.
Just to confirm, so centimeters cubed is equal to 1 milliliter, just to confirm?
Yes, so 1
Okay.
centimeter cubed is 1 milliliter.
Okay, thank you.
Okay, so this is slide 51 in my PowerPoint. Okay, this is the slide that you would need to have memorized. Okay, so this is where you're seeing right here in the center, okay, centi, the prefix centi. So a centimeter, so 100 centimeters is equal to 1 meter. The base unit is a meter. So the base unit here is, I've identified my base unit here as meter, liter, or gram. Now we already know this is a slight adjustment from the SI unit, that a gram is not technically the base unit, right? So, but when I'm calling the base unit here, it is one of these three units: meter, liter, gram. Okay, so 1 meter, okay, is the base unit here. 1 meter, and all these bottom ones here, it is 1 meter in the middle column. 1 meter. 1 meter is 100 centimeters. 1 meter is 1,000 millimeters. 1 meter is 10 to the 6 micrometers. 1 meter is 10 to the 9th nanometers. 1 meter is 10 to the 12th picometers. Okay, again, slide 51 is looking at how many of the smaller units make up the larger unit. Yes, you can take, pictures from the other camera. That's fine. All right. So let's look at a problem here where the difference between slide 51, between slide 50 and 51, right? So let's look at the difference between those two slides. All right. All right. So we're going to do this two ways. Slide 50 and slide 51. I'm not sure why it's a little blurry. Okay. So we have 67 picometers, and we want to know how many centimeters is that? How many centimeters is that? Right? So we have 67 picometers. All right. Now slide 50. Now we don't have a direct conversion of picometer to centimeter. So what we would want to do is go from picometer to meter to centimeter. Okay. So this is my method. All right. That's how I'm going to do it. In both examples here, I'm going to do picometer to meter to centimeter. Okay, I do not have a direct. Now, obviously, if you can do this and you understand the math, the logic step between picometer and centimeter, you can go, go for it. All right, but assuming we don't, I do have a conversion from picometer to meter, and I have a conversion from meter to centimeter. So what does slide 50 look like? Okay, so slide 50 is looking at how many of the larger units fit into the smaller unit. Okay, so they're saying on slide 50, they're saying in 1 picometer, there is 10 to the negative 12 meters. Okay, this is slide 50. This is not the one that I'm going to go with, but this is what slide 50 is telling us. Okay, and then there are 10 to the negative 2 meters in 1 centimeter. Okay, those are the values. Okay, those are the values off that slide. Okay, that's what that slide is telling us. How many of the larger unit fit into the smaller unit? Okay, how many of the larger unit fit into the smaller unit? Okay, so the difference of this for my slide, okay, the slide that I would go with, is this. Okay, you're not going to see different numbers, okay, but it's going to be slightly different in where they're placed. Okay, so I go by how many of the smaller units make up the larger unit. So I would say that there are 10 to the 12th picometers in 1 meter. In 1 meter, there are 100 centimeters. All right, let's take a second to absorb this information to ensure that we are not completely lost here. All right. Neither of these two calculations are going to give you the exact same number. Okay. These are going to give you the exact same number. All right. It is simply a difference. So you have to take it upon yourself to pick how you memorize the metric system. I will do practice problems based on slide 51. How many, again, my analogy yesterday was slide 50 says I can fit 12 room or 10 to the negative 12 rooms in 1 person. This slide says I can fit, 1 person, how many people do I fit in 1 room? I can fit 12 people in 1 room, right? So I am going from the larger unit, how many of the smaller units fit into the larger unit versus how many slices of the larger unit do I have to make to get the smaller unit, okay? This one here is 12 inches in a foot. This one here is how many feet in an inch, okay? That is the difference of the approach. Okay, you just have to pick a slide to memorize. Okay, memorize your metric system however you want to do it, but you're basically going to be applying one of those 2 values. Okay, so we multiply all the numbers on the top, divide by all the numbers on the bottom. Okay. Okay, so here's my value. Okay, 67 times 100. Then answer divided by 10 to the 12th. 6.7 times 10 to the negative 9 centimeters. Okay, it does not matter if we do it the other way. Okay, the top part is going to be 67 times 10 to the negative 12 divided by 10 to the negative 2. Okay, same answer. Okay, so it is just about how you set up the problem. Okay, so you pick your memorization method. Which chart do you want to go with? Okay. And I did some other practice problem videos that I will post up. Pretty sure I did at least one. I lose track now of, I keep track of all the videos that I have all the videos that I've been putting together. So I have all of them. I just have to go back and put them into the page. Okay. All right. So I am going to stop my computer or stop my phone here before it melts. Okay, turn off my phone recording. All right, so we're going to go back to the PowerPoint here. To where we left off. Okay, so again, you would start, slide 51 would be my recommendation for where you would want to start from memorizing the metric system. Okay, so we need to flashcard these, whatever you got to do to put these in your memory. Okay, you're going to need to know these units for the quiz. Okay, I will give you US units if they're needed. Okay, you don't have to memorize slide 52. Okay, question about how the quiz is going to be done. All right, so it's all in the Canvas. So basically, I will put a link. It'll be on the main front page. So it'll probably be above the syllabus and the journal article link. No, it's not going to be during lecture time. I'm going to turn it on in the morning, and you have all day to do it. So you would do it anytime during the day, and it's not going to consume lecture time. So you can do it at any point during the day, before or after lecture, at your leisure. It is timed. I will figure out how long. I will put that in the link as to how. Oh, all right. Now you're getting technical on me. All right. How many questions? I don't really remember right offhand. I'll look it up. I can't look it up right now because I have to dig into the activity. I don't know how many questions. It's not long. It's only 50 points or so. So let's see. It's probably like 11 or 12 questions. It's probably 11 or 12 questions at most. Usually the way I do it is like I said, each question is worth 4 points. So I planned the quiz around 50 points-ish. So like I said, it's either like 11 questions and it's less than 50 points, or it's 12 questions and it's worth more than 50 points, or there's extra credit built in. Yeah, there probably is. Whether it's in there for the quiz, like I said, I don't remember right offhand. Like I said, I made the first quiz a week ago and I've already forgotten. So I'll have to take a look at it. All right, so I'll have to take a look, but it's only 11 or 12 questions. It's probably an hour. to do it. In the past, I usually gave the first test was chapters 1 and 2. So in past semesters, when I have done a test of chapter 1 and 2 combined, it was only 2 hours for 2 chapters. So the tests are generally 2 hours long for 27 questions. So this is half of that, half of the points, and so usually half of the time. And it may have extra credit in there because if I made it 50 points, then that's not, it's either I made one question that's not 4 points or there's some variation of points assigned in the quiz. I'll take another look at it. Okay. So you can probably estimate right at this point, it's going to be about an hour long. It'll probably be around 12 questions. Okay. And again, very similar to the kinds of problems we've been doing. Okay. So if you can follow along with the kinds of problems we've been doing, the stuff that I've been doing on the practice problems by hand, you should be able to do those kinds of questions. Those are the kinds of questions you are likely to see. Okay. Now, also some of them are going to be measurements, the section we're just about to cover. Okay. So when we look at measurements, okay, it's just about reading the instrumentation. Okay. When we read an instrument and mark down what is the measurement on the instrument, it is just a value where sometimes we have graduations where we have to make an evaluation of the significant figures. Okay, by this I mean, okay, so think of a picture like this. Okay, this is a perfectly good quiz question. Okay, there is no calculation involved in this question. Okay, so if measurements are part of the first quiz and I give you a question like this, there is no calculation required. This does not take a minute to do. Okay. So not all of the questions are going to be calculation questions that require you to do strenuous heavy lifting of the metric system. Okay. So the question here, when we are reading this, okay, is we have to look at what are the graduations of the scale we're using. Okay. This ruler has 2 different scales on it. Both of them are in centimeters, but one of them has more graduations than the other one. Okay. This one here, you can only read by the centimeter. Okay. But we can see here that it's slightly past 4. So the rule for measurements is this. You can read 1 decimal place more than what the graduations are. Okay. What are the graduations? You can read 1 decimal place more accurate than what is marked on the glass. Okay. So by this, I mean, if it is measured in the ones place, we can read the first decimal place. Okay. This is where it is an estimation. We don't know exactly. It doesn't matter what your guess is of the decimal place. When you read this, you might read it as 4.2, or maybe you say it's 4.3, or your estimation is whatever. But the point is that you put down the decimal place. Okay. Now, On the top scale, we have 0.1, 0.2, 0.3, 0.4, 0.5. We have the first decimal place of markers. Our markers, our graduations are by 0.1 increments. So if I can read 4.1 and 4.2, I can tell if it was in between 4.1 and 4.2. If the marker was in between 4.1 and 4.2, that means technically you can read and estimate another decimal place. Okay, whatever the marking is, whatever the graduations are, you can read one decimal place more. Okay, so here we would look at the line and say, okay, it is not quite 4.1. So we would have to estimate it is before 4.1. This number is not important. It doesn't matter what your estimation is. Your estimation may be different than mine. The point is that you make the estimation, because this indicates a greater level of accuracy than this number, right? Remember, more decimal places means more accurate. Okay. Remember, we were talking about the time in the NIST clock. It reads out 13 decimal places. Okay. It keeps going out this way. There are 13 decimal places of accuracy. Okay. That's how accurate it is. This has 2 decimal places. 2 decimal places is more accurate than 1. Okay. So here would be another good test question. Okay. What is the length of the screw? Okay. Doing measurements is something that we all have to do. Okay. If you're building a deck, you got to be able to read your measuring tape, right? Because then if you don't, you're like me and you build a rickety deck that's all cockeyed because you're terrible at using tools and you're not very, and your ability to do measurements might have been perfect, but your ability to use the tools probably wasn't. So we'll blame it on the tools, not on our ability to take measurements, but we should be able to take measurements. Okay. What is the measurement that we're reading here? Okay. It reads between 1 and 2 centimeters, but it has 0.1 increments. Okay, which means we can read 2 decimal places. Your answer, especially what we're looking for on the test or for the first quiz, is how many decimal places is it going to have? Right, so the first guess would be 1.7, but remember, we can read 2 decimal places. So we've got the 0.7, but it's slightly in between. So there's 1.5. Yeah, there we go. That's a better guess. So we got 1.5, 1.6, 1.7. It's slightly more than 1.7, but not quite 1.8. So we can estimate it's that second digit. That second digit is an estimation. Now, your estimation might have been slightly different than mine, but the point is that we put the extra digit in there. Okay. This is what I'm looking for a test, for a quiz question. Okay. All right. Let's take a look at another question. Okay. When we are reading glassware that has liquids in it. Okay. The picture on the left, this piece of equipment is called a burette. Okay. If we were in the lab, we would be using burettes. Okay. This is an analytical piece of glassware that we use for all kinds of volumes. Okay. Including my favorite, which is titrations that we don't get to do in the lab, and I am salty about that. Okay. So the graduated, or the burette reads in 1 milliliter, but then it has 0.1 milliliter increments. So that means we should be able to read 2 decimal places. We read the volume from the bottom of the meniscus, the bottom of the bubble. So the bubble here is called a meniscus. So we read from the bottom of the bubble. So here, your value might be slightly different than my estimation. If we look at this as 10, so there's 10.1, 10.2, 10.3. Now, depending on how good your eyes are, we might see that it's not quite to 10.3. So I might say it's 10.28, maybe. Okay, so I might say it's 10.28, but the point is that I can read 2 decimal places. My estimation of the last decimal place is not important, but the fact that we put an estimation there. Okay, if we look at the beaker, okay, when we're in, if we were in the lab, we would use beakers. Beakers are not calibrated the same way as a graduated cylinder. So their metrics here are by 20 milliliter increments. So that means we're in the tens position of value. So here's 20 milliliters, here's 30 milliliters, here's 40 milliliters, here's 50 milliliters, 60, 70, 80. So if it's slightly more than 40, but not quite at 50, the only place we can do is estimate the single digit. We're not even at a decimal place. We cannot get a decimal place of accuracy. Okay, so you might estimate this as like 44 milliliters. Okay. It doesn't really matter. If your estimation is slightly different than mine, you would call this like 44 or 43 or 42. It doesn't matter. The point is that on the quiz, the answer is going to be chosen for you. You have to select the right number of significant figures. Okay. Because on the quiz, here's what you're going to get. Okay. Let's look at the beaker. All right. Here's the answers you're going to get. A is 44 milliliters. B is 44.0 milliliters. C is 44.00 milliliters. D is 45.000000 milliliters. Right? And so your question is, which one of those has the right number of significant figures that I can read off of this glassware? Right? And so we're going to pick A because you can't read a decimal place. It does not have 1 milliliter of accuracy, so you cannot read a decimal place. If we can't read a decimal place, then you can't say that it has more accuracy than what's on the glassware. Okay. And that is all I have for the measurements section for this chapter.
This is just an outside question. Would you be available over the weekend through email if we have questions about the lab?
Sure. Yeah. I mean, I log in every day, so I will check email every day. So if you do have questions, you can email me and we can deal with any questions that come up. Okay. All right, so that concludes chapter 1. So for the quiz next week, your main focus, all right, let's pop back over to this again. Let's look at our, don't do that. Okay, our learning objectives. Okay. I'll verify about the scientific method. I'm not entirely sure that there's questions on it, but I mean, you should be familiar with the terms. But we have metric system conversion, which includes density. Okay. Questions on significant figures. And then reading measurements. Okay. These are kind of combined. They can be. All right. But there also can be simple metric conversions like the one that we did tonight. If I give you 67 picometers, how many centimeters is that? That is a metric system conversion. Okay. The density problems, okay, given the density and the mass, what is the volume? Significant figures, looking at a basic math problem, 1.1 plus 1.25 is what? Right? How many decimal places should my answer have? Kind of thing. Okay. Reading a measurement. If I give you a picture with a scale on it, you can tell me what the measurement's supposed to be. Okay. That is the focus for our quiz for next week. Okay, questions. All right, so keep in mind, no lecture on Monday, okay? No lecture on Monday, it's a holiday. So Tuesday, we will start with chapter 2, okay? And so we'll probably pick up the pace a little bit here with some of the chapter 2, because again, I got to get through two chapters for the test, which is the following week. So again, I gotta keep pushing on target here. So about to pick up the pace just a smidge. Okay. Questions? If you have questions, I'll hang around here. Otherwise, we are done for tonight. And then I will see you guys on Tuesday. I'll be online. Don't forget the Pennies Lab is due on Sunday. Okay. Otherwise, everybody have a good night.